Imagine, if you will, the endless dark, a canvas stretching out way beyond what we can even comprehend, speckled with countless celestial bodies. Within that deep stillness, silent rocks just drift across the cosmic currents. They seem pretty insignificant, right? Just cosmic debris, maybe. But these ancient wanderers, they harbor secrets older than Earth itself. Stories of how our solar system was born, untouched by all the churning on our own planet. But it's more than just science. These silent, drifting rocks, they hold this profound, transformative potential. They might just be the future of mining, of wealth, maybe even our survival as a species. Today at Curious Minds, we're diving into one of the most thrilling and, let's be honest, controversial frontiers of science and commerce, asteroid mining.
Yeah, it's a journey that really pulls together the wildest scientific thinking with, well, almost unimaginable economic potential. And at the same time, you're navigating this complex minefield of ethical questions, practical problems. Our ambition here in this deep dive is to really get a handle on how we might bridge that gap. From Earth, where resources are getting tight, to potentially unlocking quadrillions of dollars out there in space. We'll meet some of the fascinating people involved, unpack the really cutting-edge tech that's slowly making this real, and face up to the big questions this whole new frontier forces us to ask. So get ready, because the future of resources might just be, well, literally out of this world.
Okay, so to really get why asteroid mining is such a big deal, this ambitious idea, we kind of have to start right here on Earth. Our planet, amazing as it is facing some pretty serious resource challenges, no denying that. We live in a world where the demand for essential elements, the stuff that fuels modern life, is just growing like crazy, exponentially. Think about your phone, electric cars, medical tech saving lives, the green energy solutions we desperately need.
Right. All of those depend heavily on elements like platinum, cobalt, gold.
Exactly. And these aren't just, shiny things. They're the fundamental backbone of our tech, our industry, and the cost of getting them. It's not just money, though that's huge. It's also severe environmental damage and increasingly tricky geopolitical friction.
It's really striking, isn't it, how Earth's resources, which maybe we once thought were limitless, are now clearly showing their limits. Terrestrial mining, the way we do it now, it comes with an incredibly high price, a price we can't ignore. Just think for a second about the environmental devastation. Current mining practices, they lead to significant, often permanent habitat destruction. Whole forests gone, mountains stripped bare, unique ecosystems just altered forever. And then there's the pollution, air, water. Mining often uses really dangerous chemicals, cyanide, sulfuric acid, chlorine to get the minerals out. And those chemicals, they inevitably end up contaminating local water, poisoning the air. You can see the impact visually. Just look at satellite images. Huge open pits, toxic tailing ponds, massive piles of waste rock. Scars on the landscape that last for generations.
It's a grim picture.
It is. Now, if you contrast that with asteroid mining, well, it could emerge as an environmentally more attractive option, especially compared to things like deep-sea mining, which carries its own terrifying ecological risks. And this is a really important but, we have to listen to experts like Professor Monica Grady. She raises genuine concerns about, quote, tarnishing space's pristine environment.
Right, we don't want to just move the problem somewhere else.
Exactly. Her point isn't just philosophical, it's practical. She emphasizes how crucial it is that we learn to clean up as we go along. We absolutely must not let space become another dumping ground. We need sustainable practices right from the start.
Makes sense?
And beyond the environment, there are the social justice issues. Terrestrial mining operations are often plagued by really dangerous working conditions, injuries, illnesses, even fatalities. Plus, these projects often displace entire communities, uprooting people from their homes, destroy livelihoods, eroding culture. It's about basic human rights.
Yeah, that's often overlooked.
And finally, the fact that these valuable minerals are finite and often found in just a few places, that directly fuels geopolitical tension, even conflict. Countries get locked into this fierce competition for resources, leading to instability, proxy wars, a constant struggle for economic power.
So all these challenges kind of force us to think bigger, don't they? It brings us to this philosophical point, really. That quote sums it up. There's infinite space out there and countless asteroids, but only one Earth.
Precisely. It pushes us to reconsider humanity's long-term sustainability.
And this idea isn't entirely new, right? People worried about running out of resources before, like Malthus.
Right, Thomas Malthus, way back in 1798, he had that famous theory that population growth would eventually outstrip resources, leading to famine and collapse. Thankfully, humanity's been pretty ingenious. We've adapted, invented new farming techniques, found new energy sources. We've defied those predictions so far.
But is it different this time? The scale seems bigger.
The context is different, and the scale is just unprecedented.
Hmm.
Think about it. Between 1800 and 2000, the global population jumped sixfold, a billion to 6 billion people.
Wow.
And our energy consumption, it increased 30-fold in that same time. 30. Looking ahead, the UN projects will hit 9.7 billion people by 2050.
So the pressure is just immense.
Immense. And combine that with how much harder and more environmentally costly it's getting to extract what's left on Earth, well, it makes the need for alternatives incredibly urgent. It's not just academic anymore. It's becoming, you could argue, an existential necessity.
Okay, so Earth's limitations are becoming clearer. What about space then? What's the potential out there? Asteroids. They're not just rocks, you said.
Not at all. For most people, maybe they're just distant objects or movie threats. But there's so much more. They are essentially leftover bits from when the solar system formed.
Like cosmic crumbs?
Kinda, yeah.
Yeah.
Like the baker finished making the planets, and these are the valuable ingredients left over, unused.
And you mentioned a key difference in where the metals are compared to Earth.
Exactly. On Earth, when it was forming and super hot, gravity pulled the heavy stuff, most of the metals, down to the core, where we basically can't get to it.
How much are we talking about?
Get this. Roughly 99% of all the gold on Earth is locked away in the core. Enough, theoretically, to cover the entire planet half a meter thick.
That's unbelievable, but asteroids are different.
Yeah, because they weren't massive enough for that same intense gravitational sorting to happen. So the valuable metals, other elements, they're spread around much more evenly, closer to the surface, theoretically easier to access. They really are like floating treasure chests.
So what kind of treasure are we talking about? How much is really out there?
Well, the potential wealth is just staggering. But first, it helps understand the different types, the different flavors of asteroids. There are mainly three kinds. First up, you have the C-type, or carbonaceous asteroids. They're the most common, over 75% of known asteroids.
Carbonaceous. So carbon.
Rich in carbon, yes, but also water and organic compounds. Chemically, they're a bit like the sun, but without the hydrogen, helium, the really volatile stuff. And their big value isn't just metals, it's water. Huge amounts of water ice.
Water in space. Why is that so important?
Because you can use it, process it into rocket propellant, use it for life support for astronauts, even radiation shielding. Imagine having refueling stations in orbit made from asteroid water. It could totally change space travel.
Wow. Okay, so C-types are water-rich. What's next?
Next are the S-type, or stony asteroids. They make up about 17% of the asteroids we know. These are those with valuable deposits of things like nickel, iron, platinum, magnesium, silicates.
So more metallic.
Right, more rocky and metallic content. Prime targets for certain industrial needs. And finally, the rarest, but potentially the most valuable, the M-type, or metallic asteroids.
Metallic monsters, you called them.
Yeah, that's a good way to put it. They're basically the exposed metal cores of ancient protoplanets that got smashed apart billions of years ago. These could hold more iron and precious metals than Earth's entire crust.
Seriously, like what?
Take 21 Lutetia. It's an M-type, about 75 by 60 miles. The Rosetta probe flew by it in 2010 and confirmed it's loaded with metals. Or 216 Cleopatra, that's the really weirdly shaped one, like a ham bone, right?
Yeah.
About 135 miles long. And it even has two tiny little moons. Radar images showed its metallic nature.
How do they even know what they're made of from so far away?
It's pretty clever, actually. They use telescopic spectroscopy, basically analyze the sunlight that reflects off the asteroid's surface. Different minerals reflect light differently, creating a unique fingerprint. Let's just get a good idea of the composition without even touching it.
Okay, so spectroscopy tells us what's there. Now, the big question, what's it all worth?
This is where the numbers just get insane, jaw-dropping, really. Moving from billions to, well, quadrillions. Consider this. Even a relatively small asteroid, say 30 meters across, if it's rich in platinum, it could be worth $50 billion.
50 billion for one small rock.
Yep. But that's peanuts compared to big ones, like the M-type asteroid 16 Psyche. It's huge, mostly metal. Estimates suggest it might hold wealth in the quadrillions of dollars.
Quadrillions. I can't even picture that number.
It's mind-boggling. And it creates this huge economic paradox, almost a philosophical question. Is that enough wealth to, quote, make everyone on Earth a billionaire? Maybe. Or would it just crash the entire economy by flooding the market with metals that used to be incredibly rare?
That's a wild thought. Crash the economy.
Potentially, yeah. If you suddenly make platinum as common as aluminum, what happens to the value? And the scale goes even higher. The Vita, a really big asteroid in the main belt, maybe 300 kilometers across. Its combined resources are estimated somewhere around $27 quintillion.
Quintillion. Okay, my brain just broke.
Yeah.
Yeah.
It's not just about profit. It's about fundamentally changing global economics, changing the meaning of rare.
Mm-hmm.
And we've already identified specific targets nearby, relatively speaking.
Mm-hmm.
Near-Earth asteroids, NEAs, and short-period comets. There are over 20,000 NEAs and 100 comets cataloged as potential targets.
Any specific examples?
Sure. Take Ryugu. It's an NEA. Orbits not too far from Earth's path. Estimated value. $83 billion USD in nickel, iron, cobalt, water, nitrogen, ammonia. And Japan's Hayabusa 2 probe has already visited, surveyed, and brought back samples.
So you actually touched that one.
We have. Then there's Bennu, another NEA, maybe $700 million worth of iron, hydrogen, ammonia, nitrogen. And that's the one NASA's OSIRIS-REx visited and brought back a big sample from. Didymos, another one, potentially hazardous, actually, orbits a bit further out. Estimated $62 billion in nickel, iron, cobalt. And maybe the biggest nearby prize is Antares. It's over a mile wide, orbits about 1.4 times Earth's distance from the sun, potential value. An estimated $5.57 trillion USD in magnesium silicate, aluminum, iron silicate.
5.5 trillion from one asteroid.
Exactly. These aren't just distant abstract rocks. They're tangible, potential economic game changers right in our cosmic neighborhood. They promise to reshape industries and maybe redefine scarcity itself.
And that really is the aha moment, isn't it? The sheer vastness of space, plus the unique way asteroids formed. It equals this treasure trove beyond anything we've imagined. It's not just about finding more stuff. It could completely upend the whole idea of scarcity that's driven human economics forever. What happens when rare isn't rare anymore? Okay, the numbers are just incredible. The potential's huge. The vision is, yeah, it's compelling. But like anything that promises that much wealth, there's always a catch, right? A flip side. This immense promise seems tangled up with equally immense risks.
Absolutely. It's a fundamental paradox. Which leads us to a really critical question. Could asteroid mining, this thing that promises so much, actually trigger a devastating market collapse back here on Earth?
How would that work?
Well, think about a really successful mission, especially one targeting something super valuable now, like platinum or gold. If you suddenly bring back tons of it, you could literally flood Earth with metals and trigger a massive market collapse. Remember Psyche 16? The one with potential quadrillions in minerals. If you actually extracted that on a large scale, it would almost certainly crash the world market for those minerals.
So making something abundant makes it cheap.
Drastically cheap, potentially overnight. And the consequences wouldn't be abstract economic theory. They'd hit developing countries hardest, countries whose economies depend heavily on exporting those same minerals mined from Earth.
Like who?
Take South Africa. Back in 2018, they produced 72% of the world's platinum. 72%. That was worth $3.8 billion, supported nearly 500,000 jobs, and made up over 8% of their GDP.
Wow, that's huge reliance.
Huge. Now, imagine space mine platinum floods the market. South Africa's economy wouldn't just shrink. Experts say it would shrivel. That could be devastating for millions of people, destabilize the whole country. Same goes for Zimbabwe, another big platinum producer, or the Democratic Republic of the Congo, which relies heavily on cobalt. These countries often lack the resources to just pivot and develop their own space mining tech.
So they'd be left behind, economically ruined.
It's a serious risk. And it also raises the possibility of maybe just one company ending up controlling the entire global supply of a vital resource. That creates a totally new kind of economic vulnerability for whole nations, shifting global power in unpredictable ways.
Okay, so market collapse is one big risk. What else? You mentioned investment problem.
Yeah, that's the classic chicken and egg dilemma for this whole industry, basically. No one wants to invest in space mining when no one is buying space resources yet.
Ah, the catch-22.
Exactly. Even if there are theoretically quadrillions of dollars out there, those billions of dollars worth of valuable resources in space are worthless if it costs trillions to get them.
Right. That has to make economic sense.
Precisely. Think about the gold in seawater. There's an estimated 20 million tons of it, technically worth $750 trillion.
Yeah.
But filtering it out costs way, way more than the gold is worth. So nobody does it. Same principle applies to asteroids. The value is only real if the cost of access is manageable.
And the costs for asteroid mining are high.
Astronomical is the word. One study estimated $2.6 billion, billion dollars with a B, just to tow a 500-ton asteroid back to orbit.
Just to tow it, not even mine it.
Just the towing. That's just one early step. Now look at a company like Astroforge. Their near-term goal is ambitious, but seems almost modest in comparison. Bring back about 1,000 kilograms, that's 2,200 pounds, of platinum group metals per mission. Depending on the market, that could be worth around $70 million. Their CEO, Matt Gielich, put it very bluntly. This actually is not a question of if it can be done from a physics standpoint. It's a question of can you do it so it makes any monetary sense.
So feasibility isn't just physics, it's economics.
That's the core challenge right now. Can you make the business case close? And history here isn't super encouraging. Even big, well-funded ventures have struggled. Remember Planetary Resources? Launched in 2012, $50 million from big names like James Cameron, Larry Page.
Yeah, I remember the hype around that one.
Huge hype. But they faced funding difficulties. Ended up getting acquired by a blockchain firm in 2018, hardware auctioned off by 2020. Same story, basically, with Deep Space Industries, DSI. Founded 2013, raised $3.5 million, acquired by Bradford Space in 2019. The general feeling among experts is pretty clear. Interest is high, sure, but some companies are going to fail, some business cases are not going to close. It's just a really tough, high-risk business.
So where does that leave things? Is anyone actually making progress?
Well, it's led to a bit of a shift. The immediate focus for space resources seems to be moving towards the moon. It's closer, the challenges are maybe a bit more manageable in the near term. Asteroids are increasingly seen as a much longer view, maybe decades before we see large-scale commercial mining.
Right, so the moon first, then asteroids later.
That seems to be the emerging roadmap for many.
Which leaves us with this massive question hanging over everything. Is asteroid mining going to spark a new gold rush, create incredible wealth and innovation? Or could it fundamentally break the whole concept of scarcity, changing our economies and societies forever? It feels like it could go either way.
Okay, let's shift gears a bit. We've talked about the potential riches, the massive risks. Now let's get into the nitty-gritty.
Yeah.
How do you actually do this?
The engineering, the practical challenges of mining in space. This is where it gets really wild, right? Because the whole vision depends on engineering breakthroughs that honestly sound like something straight out of science fiction. We're talking about making the impossible possible.
Absolutely. The technical hurdles are just monumental, and they start with the asteroids themselves. See, most asteroids aren't solid rocks like you might imagine. They're actually rubble piles. Think of a giant collection of gravel and boulders loosely held together by their own very weak gravity.
Like a cosmic sandcastle.
That's a great analogy. And that structure makes mining incredibly difficult. Traditional methods, drilling, blasting with explosives, even just using heavy equipment could just break the whole thing apart, send valuable material flying off into space.
So you can't just land a big drill on it.
Not easily. In microgravity, any force you apply could have unpredictable results. Dislodged debris could shoot into space at high speed, becoming dangerous projectiles for other spacecraft or equipment. And imagine being a space miner out there. The personal challenges are immense. You must tether themselves to avoid floating off into the void constantly. It's physically demanding, psychologically taxing, working in a truly alien environment.
Wow. Okay, so standard mining is out. What's the alternative?
Well, the thinking is we'll need a huge orbital infrastructure. We're talking gigantic orbital factories and refineries, facilities built in space specifically to process asteroid material right there.
Process it in space, not bring the raw rock back.
That's the idea, to avoid hauling back tons of worthless rock. The proposed methods are pretty ingenious. Picture huge mirrors, maybe kilometers wide, focusing sunlight.
Like a giant magnifying glass.
Exactly. Heating up the asteroid rock so intensely that it boils out the gases, separating the volatile elements like water. Then, maybe massive grinders break up what's left the dried rock into gravel and dust for further processing.
And the water you boil out. You mentioned using that.
Yes, that's the concept of in-situ resource utilization, ISRU. Using resources found in space to support space missions. That water ice from C-type asteroids. You split it into hydrogen and oxygen, and boom, you've got rocket fuel.
Made in space.
Made in space. You can also use the water for life support or even as radiation shielding. It could drastically cut the cost of long missions because you don't have to launch everything from Earth's deep gravity well.
That sounds like a game changer.
It really is.
Yeah.
Even though building that initial infrastructure costs a fortune, ISRU could make sustained space exploration and industry much more feasible in the long run. There's even talk of ferrying mined materials to the moon for refining. The moon's low gravity and lack of atmosphere make it potentially easier to process things and launch them elsewhere.
So who's actually building this sci-fi tech? Are companies making progress?
They are. Astroforge, for instance, is pushing boundaries. They actually sent a small refinery unit into orbit in 2023. That's a huge step.
A refinery in orbit? Wow.
Yeah, and they're planning another mission in 2024 to photograph a metallic asteroid using AI tracking. Their core tech is this metal vaporization process. They use things like inductive heating to vaporize specific metals, like iron, right off the asteroid in orbit.
Vaporized metal
Mhm.
in space.
Right. Then they condense just the pure, valuable metal, leaving the waste rock behind. Brings back a much more concentrated, valuable payload. They even use sophisticated models like ion-resistant cycling to optimize it. Their first mission, Odin, had some communication issues, but its goal was to test tech for assessing asteroid 2022 OB5. So real hardware, real tests.
Okay, that's pretty cool. Anyone else?
Definitely. TransAstra, that Houston company. Their founder, Joel Sarcel, is pretty confident they've cracked some key technical problems. They've got a whole suite of tech, like their inflatable capture bag technology. Originally for grabbing space debris, but you can imagine using it to enclose a small asteroid for mining. They're planning an ISS demo for that.
An inflatable bag to catch an asteroid.
Sort of, yeah. And they're also revolutionizing how we find asteroids with their Sutter-Mill telescopes. It's a network of low-cost telescopes using really smart software-optimized matched filter tracking to spot small asteroids, 15 to 50 feet across. They hope to find hundreds of times more asteroids a year this way.
Finding the targets is key, I guess.
Crucial. And their APIS flight system includes concepts like the Omnivore thermal rocket for efficient travel, the Mini-Bee, a small 550-pound robotic miner demo, and plans for bigger bee systems to capture asteroids up to 40 meters wide. Plus, they have this trademarked optical mining technique, using concentrated sunlight, like what he talked about, to basically dig into volatile-rich asteroids and extract propellant, like water, using the sun's energy directly.
Sunlight as a mining tool. Amazing. What about getting all this stuff to space? Launch costs used to be the killer, right?
Absolutely, and that's where reusable rockets like SpaceX's Falcon 9 have been totally transformative. They are dramatically slashing costs for getting mass into orbit, making these ambitious asteroid ventures seem much more economically plausible than they were just a decade ago.
Cheaper launches make everything else more possible.
Exactly. And for the long journeys out to the asteroids, there's a lot of potential in scaling up electric spaceships, things like ion thrusters or Hall thrusters. They don't have the raw power for launching from Earth, but once you're in space, they're incredibly fuel efficient. They need only a tiny amount of fuel to go very far, which means huge savings on propellant for those long trips, cheaper access to orbit, plus more efficient travel in space. That's the foundation.
And we have actually brought bits of asteroids back, right? This isn't purely theoretical.
Not purely, no. National space agencies have already proven the concept. Japan's JAXA was the real pioneer with Hayabusa 1 back in 2005, returning dust from Itokawa, and then Hayabusa 2 in 2014, bringing back samples from Ryugu.
Tiny samples, though.
Initially, yes. Hayabusa 1 got only micrograms,
Yeah.
but Hayabusa 2 got several grams. And then NASA's OSIRIS-REx mission, launched in 2016, hit the jackpot. It returned its sample from asteroid Bennu in 2023, and it was at least 400 grams.
400 grams. It's almost a pound.
Yeah, a new record by far. Before OSIRIS-REx, humanity had only retrieved about a gram total from asteroids. So this was a massive leap. And these missions, even though they're expensive, OSIRIS-REx cost over $1 billion, they're not just about the science, studying the early solar system. They are crucial test beds. They teach us how to navigate to these tiny bodies, match speeds, orbit them, land on weird, rubbly surfaces. All essential skills for future mining. They're laying the practical groundwork.
So the tech challenges are still immense. Sounds like something out of a movie sometimes. But human ingenuity is chipping away at it piece by piece, turning this wild dream into something that feels maybe possible. Okay, so it's not just about the tech and the asteroids themselves. As this whole field starts to take shape, there's this whole complex web of players involved, right? National space agencies, private companies popping up even, space lawyers.
It's becoming a crowded field with a diverse cast of characters, all with different motivations and interests. And it's all unfolding against this backdrop of evolving and sometimes conflicting legal and political frameworks.
Let's break that down. Who are the main government players?
Well, NASA's obviously a huge one. They're actively exploring asteroids, not just for science, but with an eye on resources too. We mentioned their Psyche mission heading to the metal asteroid 16 Psyche, due to arrive around 2026. That's pure resource assessment. And OSIRIS-REx, bringing back that big sample from Bennu, gives them hands-on experience. Plus, NASA's heavily involved in planetary defense. Things like the NEO Surveyor telescope launching soon to find dangerous asteroids, and the DART mission that actually hit an asteroid to change its path.
Right, the DART mission was amazing.
It was. And while its main goal was defense, learning how to interact with and move asteroids has obvious overlaps with potential mining techniques down the road.
What about other countries?
Oh yeah, it's definitely global now. Japan's JAXA, as we said, pioneered sample return with Hayabusa 1 and 2. They proved it could be done. China, CNSA, has really ambitious plans. They've got Tianwen-2 launching around 2025 to grab samples from a near-Earth asteroid and bring them back by maybe 2027. Even the United Arab Emirates Space Agency is getting in the game. Their MBR Explorer mission is set to launch in 2028 to explore the main asteroid belt. It signals that this isn't just a US-Russia-China thing anymore. And you also have nonprofits like the B612 Foundation, founded by scientists and astronauts working on planetary defense, mapping asteroid threats with tools like their Atom platform. It all feeds into the same pool of knowledge about asteroids.
Okay, so governments are definitely in. What about the private sector, the startups?
That's where a lot of the really dynamic action is. We talked about Astroforge, setting up their test refinery, planning missions to image metallic asteroids, aiming to bring back platinum group metals this decade. Their CEO is really driving that commercial focus.
They seem pretty serious.
They do. Then you have companies like Kepler Energy and Space Engineering. They're projecting autonomous mining robots, pulling tons of regolith off small NEAs by the end of the decade. Interestingly, their main focus isn't just precious metals. It's water for ISRU.
Water as the first big commodity.
Could be. And Transastra in Houston, building that transcontinental railroad of space with their mini-B miner concept and optical mining tech. They have a very integrated vision. But we also have to remember the cautionary tales. Planetary resources, deep space industries. They had big ambitions, big names, significant funding, but ultimately didn't make it as independent companies. It underscores the huge financial risks involved. It's not an easy business to crack.
So where are they all looking to mine? You mentioned near-Earth asteroids.
NEAs are definitely the prime targets for now. They're just easier and cheaper to get to. Lower delta V, as space engineers say, less change in velocity needed. But longer term, there are other interesting ideas, like using Photos, Mars's biggest moon. Because it's in a synchronous orbit, some see it as a potential space elevator for Mars, a staging point.
A space elevator? Seriously?
Oh, conceptually, a base on Phobos could make accessing Mars much easier, and it could also be a great jumping-off point for missions deeper into the main asteroid belt between Mars and Jupiter. That's where the truly vast reserves are, the ultimate long-term prize.
Okay, so we have governments, companies, locations, now the lawyers. How does space law handle owning an asteroid, or the stuff you mine from it?
Ah, yes, the space lawyers. It's a fascinating and crucial area. The bedrock is the Outer Space Treaty of 1967. Ratified by 115 countries, it treats space as a global commons, like the high seas. Crucially, it prohibits claiming celestial bodies through national sovereignty. You can't plant a flag and say, this moon is mine.
Okay, so no country can own an asteroid.
Right, but here's the key ambiguity. The treaty doesn't explicitly ban resource extraction. It's silent on that. The generally accepted interpretation, especially by countries pushing forward, is that while you can't own the land, you can own the resources you extract from it.
Like fishing in international waters. You don't own the ocean, but you own the fish you catch.
That's the common analogy, yeah. Once you remove the resources, they become your property to possess, sell, trade. Now, there was an attempt to clarify this. The Moon Agreement of 1979. It said lunar resources shouldn't be anyone's property and exploitation should be governed by an international regime.
Sounds more comprehensive.
It does, but almost nobody signed it. Only 7 states ratified it, and none of them were major spacefaring nations. No U.S., no Russia, no China. They didn't like the idea of mandatory resource sharing or needing international permission. So the Moon Agreement is largely irrelevant in practice.
So without clear international rules on owning resources, what happens?
Nations started making their own rules. The U.S. Space Act of 2015 was huge. Signed by Obama, it explicitly grants U.S. citizens the right to own space resources they obtain. It basically said if a U.S. company mines it, they own it, and it encouraged commercial activity.
That sounds like a green light.
It absolutely was. And later, U.S. executive orders under Trump reinforced this, saying the U.S. doesn't view space as a global commons for resource purposes and actively encouraging private recovery, basically ending decades of legal ambiguity from the U.S. standpoint. And it wasn't just the U.S. Luxembourg jumped in early, back in 2016. They created their own legal framework to attract space mining companies, offering financial incentives, signing deals with Japan, Portugal, the UAE, positioning themselves as a hub.
So different countries are making their own rules. What does that mean globally? Could it cause conflict?
That's the big worry. This patchwork of national laws, combined with a lack of broad global consensus, could spark diplomatic or even corporate wars over off-world claims. National interests are clearly driving countries to interpret space law in ways that favor their own industries, essentially incentivizing commercialization. It makes it pretty clear that, ready or not, asteroid mining is going to happen, legally sanctioned or not by everyone. There is a UN Special Committee meeting planned for 2027 to discuss space resources, but anything they come up with won't be legally binding. So the race seems likely to continue, driven more by national ambition than collective agreement for now.
Wow. It really is a complex mix, isn't it? Incredible ambition, amazing innovation, but bumping up against this urgent need for international rules and ethical guidelines. And it feels like the rules are being written on the fly, often by those most eager to start digging. The potential for future friction seems pretty high. So we've covered a lot of ground: the huge potential, the scary risks, the mind-bending tech, the players, the politics. Where does this all leave us? Let's zoom out and think about the really big picture, the long-term implications for humanity, for our future.
Right. Looking ahead, it really highlights this dual nature of how we interact with asteroids. We see them as resources, but messing with them, especially moving them around near Earth, well, that might pose a collision hazard threat. That's something scientists like Carl Sagan and Stephen Ostro warned about years ago.
So trying to mine them could accidentally cause one to hit us?
It's a non-zero risk, especially if you're talking about altering orbit significantly. It creates this incredibly delicate balance. As some experts put it, if controls instituted on orbit manipulation technology were too tight, future spacefaring could be hampered. But if they were too loose, human civilization would be at risk.
Walking a tightrope.
Exactly. NASA's DART mission, hitting that asteroid Dimorphos, was amazing proof we could nudge an asteroid. But it also underscores this immense responsibility involved and the potential for unintended consequences if we're not extremely careful.
Okay, so planetary defense is linked. What about environmental concerns in space? We talked about not trashing space like we have Earth.
That's a huge one.
Yeah.
A major concern is space tailings, basically. The leftover rubble, dust, and waste rock from mining operations. What do you do with it? There's the problem of just waste disposal in space, and the worry that maybe some of this debris might eventually fall to Earth creates new risks.
And dust. You mentioned dust earlier.
Yes, mining is expected to generate tons of fine, abrasive, sticky dust. We saw how much trouble lunar dust caused the Apollo missions, gumming up mechanisms, reducing visibility, even potentially being a health hazard for astronauts. Asteroid dust could be just as bad or worse. It could coat solar panels, clog equipment, create a hazardous environment for nearby spacecraft or future settlements.
So space could get messy.
Very messy. And that feeds into the larger problem of space debris, which asteroid mining could dramatically worsen. We're talking about triggering or accelerating Kessler syndrome.
That's the cascading collision thing.
Right, where one collision creates debris, which causes more collisions, creating more debris, a chain reaction that can make certain orbits totally unusable for generations. Imagine losing access to low Earth orbit. That disrupts GPS, communications, weather forecasting, essential services we rely on daily. It could cause significant global instability. And the European Space Agency already tracks over 36,000 objects bigger than a softball in orbit. Adding mining debris without careful management is a recipe for disaster.
We definitely need rules for cleanup then.
Absolutely. And rules to prevent contamination too. Spills or accidents during mining could permanently damage these unique asteroid environments, much like irresponsible mining has damaged Earth. We need strong safeguards and contingency plans right from the start. Plus, many asteroids are scientifically priceless. They're relatively untouched time capsules from the solar system's formation. They hold clues about how planets formed, where water came from, maybe even the origins of life.
So mining could destroy scientific value.
It absolutely could. Permanently alter their physical and chemical makeup, erasing that history before we fully understand it. There are planetary protection guidelines from COSPAR to minimize biological contamination, but enforcing them with lots of commercial missions, that's going to be a huge challenge.
Are the mining techniques themselves sustainable?
That's another question. Some proposed methods, like pneumatic excavation using gas jets, need a lot of energy and could create debris clouds. Thermal extraction, heating, is energy intensive. Chemical extraction could produce harmful byproducts. Even electrostatic separation needs significant power. We need to think about the long-term energy footprint and waste streams. And fundamentally, mining will change these bodies. The geological features that tell us about the solar system's history could be altered permanently, maybe even affecting their suitability for future human habitats or science outposts.
Okay, so
Yeah.
weighing all that, what's the ultimate verdict? Utopia or instability? Where does asteroid mining take us?
That really is the grand dichotomy, isn't it?
Yeah.
Will it either usher in a post-scarcity utopia or bring unprecedented instability to our global economy, and maybe even our environment and space. You can paint a really hopeful picture, a future where landscapes on Earth, ravaged by mining pollution, finally get a chance to heal, where the tech wonders we rely on get cheaper, cleaner to make. Imagine a future where the space industry grows, materials become abundant, and maybe, just maybe, we could eventually stop mining on Earth altogether. Let our planet recover.
This sounds pretty good.
It does. And the key takeaway for me is that this future, it's not science fiction in the sense that we need brand new physics or unobtainium. The basic principles, the foundational tech, it's largely here or rapidly developing. We could start building this future today. All it really needs, perhaps, is that initial sustained push. Investment, political will, international cooperation.
So as we stand here, looking out at this incredible new frontier, knowing the potential, knowing the dangers, we're left with a really fundamental question, aren't we? Why are we reaching into space? Is it pure curiosity? Is it sheer necessity because we're straining Earth's resources? Or is it greed? Is this quest for asteroid treasure a bold, necessary next step for humanity? Or is it just another chapter in the long story of human overreach, maybe repeating old mistakes on a cosmic scale? Thank you for being on this trip with us. Stay curious, stay grounded, and stay tuned for the next one.